All right, good morning, good afternoon, and good evening, everybody. Today we're going to talk about combinations and sample space. So, as with a lot of the stuff that we're learning in our probability unit, understanding the vocabulary is super important. So, we really want to make sure that we understand what these words are talking about so we can understand the questions and how to answer them. So the first thing we're going to talk about is a combination. So that's today's lesson. So a combination is a collection of things in which the order does not matter. So that's the key here, that the order does not matter. So when we're combining things, that the order in which I put them doesn't matter. So for example, if you're making a sandwich, how many different combinations of two ingredients can you make with cheese, mayo, and ham? So for example, if I'm putting a sandwich together, if I do the cheese first and then the ham, the order does not matter. If I put the ham and then the cheese, or cheese and then the ham, I'm still making the same sandwich. I could also put together the cheese and mayo, right? Because we're only putting two ingredients together. And so that's the same thing as if I had put mayo and cheese. So the order is not a big deal. So then really my only other combination here would be to put mayo and ham together. Because if I were to look at any other possible combination of these three items as a pair, I would really be looking at one of these combinations, right? So cheese and ham, ham and cheese, those are the same. Cheese and mayo, mayo and cheese, those are the same. Mayo and ham, ham and mayo, those are the same. So the order of those two ingredients doesn't matter to make our combination. So what we're looking at here when I list these out using the abbreviations, we're talking about our sample space. And so this is a set of all possible outcomes or results, and we can show it using a tree diagram or a list. So what I have made here with my letters is really a list, and what we see over here is what's called a tree diagram. Now it's called that for obvious reasons, hopefully, that it's going to show all of our possible outcomes or results using branches coming out for every option. So that's where the name tree diagram comes from, because it looks like we're branching out, right? Mathematicians aren't the most clever in naming things. So what we're seeing here in this tree diagram to the right is that we could pick blue pants or black pants, and then we have three options for our shirts to make combinations of outfits, right? So I could pick the blue pants with the gray shirt, blue pants with the yellow shirt, blue pants with the red shirt. Or if I had started with black pants, I could put the black pants with the gray shirt, black pants with the yellow, or black pants with the red shirt. And so I'm seeing all of those different options spread out here. So tree diagrams are usually really nice ways to visualize all of our combinations, but they're really much more efficient when we're working with smaller sample spaces, right? So I'm just talking about 2 pairs of pants and 3 shirts that I could pick from. If I had like 10 pairs of pants and 15 shirts, I wouldn't want to have to draw out, 15 branches off of those 10 original items. So that could get kind of crazy. So what we can do when we're looking for how many combinations for bigger sample spaces is we can use what's called the counting principle. So this is used to find the number of possible outcomes. And so it states that if an event has m possible outcomes and another independent event has n possible outcomes, then there are m times n possible outcomes for the two events together. Or you simply multiply those number of outcomes together. So for example, in this picture here, we have 2 pairs of pants that we could pick from, 3 shirts that we could pick from, and 2 pairs of shoes. So to figure out all of my possible combinations, I would do 2 times 3, giving us 6, and then multiply by the 2 for the shoes to get 12 combinations. So that's a really quick way of figuring out how many combinations I have without having to make that tree diagram of, so let's say, pants 1 and pants 2, and then I would have my shirt 1, shirt 2, shirt 3, and I'd have to do that again here. And then I would have another branch for my shoes, so I'll use SH for shoes. All right, and so quickly you're going to see why doing the counting principle here would be a little bit nicer, because I'm actually going to probably run out of space here. All right, so I have 1 and 2, 1, 2, 1, 2. So I got a little sloppy there and a little shorthanded. But you guys get the idea that using the counting principle to figure out that there's 12 combinations is way quicker here than doing the tree diagram. Now, could I do a tree diagram? Absolutely. And that would be really nice if I wanted to see specifics of, that combination of pants 1 with shirt 2 and shoes 3 or choose 1, right? So I can see those specific combinations written out in the list, but if I want to know how many combinations, the counting principle is going to usually be a little bit quicker. All right, so let's look at some examples. So here we want to draw a tree diagram that shows how many meal combinations you can make with 3 choices of appetizers, 2 entrees, and 3 desserts if you're going to pick 1 appetizer, 1 entree, and 1 dessert. So let's say you go out to dinner and you want to know how many choices you could possibly make. So we would start with our appetizer 1, appetizer 2, and appetizer 3. So I have those 3 choices that I could pick for an appetizer. Now, let's say I picked appetizer 1, then I have my choices of entree 1 or entree 2, right? We have 2 entrees to pick from. If I had picked appetizer 2, I could have then also, again, picked from either entree 1 or entree 2. And if I had picked appetizer 3, I would have had the choices of entree 1 or entree 2. Now, I'm going to break this even further into the fact that I have 3 different desserts. So I could pick from dessert 1, dessert 2, dessert 3. I'm going to make 3 branches here. Dessert 1, dessert 2, dessert 3. And we're going to really see that this can get kind of filled in pretty quickly. Dessert 2, dessert 3. And so I'm going to keep making these branches for each of my options. So again, this can be a little time consuming for us to make, but we're going to be able to see what our possible combinations could possibly be. Nice and visual here. And there's my final dessert 3. So I want to know how many possible combinations could I have? Well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I have 18 combinations. Now, if you're sitting there going, well, Mrs. Murphy, if it just wanted you to know combinations, why would we make this tree diagram? Why wouldn't we just use the counting principle? Well, we absolutely could, right? So here, the counting principle, we want to use the counting principle to show how many meal combinations you could make, again, with those 3 choices of appetizers, 2 entrees, and 3 desserts, if you're picking 1 of each. So what we're going to do is we're going to do the number of appetizers first times the number of entrees, and then multiply by the number of desserts. So 3 choices of appetizers, 2 choices of entrees, and 3 choices of desserts. 3 times 2 giving us 6, times 3 again is going to give us those 18 combinations. So if I just wanted to figure out how many combinations, counting principle is definitely a little bit quicker. But let's say I wanted to know more information about this. Like let's say I wanted to say how many options do I have that are going to, let's say, give me dessert 3, right? So how many combinations could I have that are going to include dessert 3? So I could pick appetizer 1, entree 1, and dessert 3. I could have picked appetizer 1, entree 2, and dessert 3. Appetizer 2, entree 1, and dessert 3. Appetizer 2, entree 2, dessert 3. Appetizer 3, entree 1, dessert 3. Appetizer 3, entree 2, and dessert 3. So what I'm seeing is that I have 1, 2, 3, 4, 5, 6 out of my 18 that include dessert 3. So I could say, I want this. I could say that dessert 3 in, what did I say? 6 out of 18. So that would be actually 1/3 of our options, right? 1/3 of our options will have dessert 3. So when we see it visually, we can get those probabilities and see it a little bit clearer. Or if I want to just know how many combinations total, that's where I would use the counting principle. All right, so let's do this again. So we want to draw a tree diagram here, so they're specifically asking us for that, to show the sample space of all the outcomes of flipping a coin 3 times. So here I just want to show my sample space. So I want to know what are all my possible, not necessarily the number of possible outcomes, but I want to see visually that sample space. So let's think about it. What are my possible outcomes for flipping a coin? Well, I could land on a head or I could land on tail. So I could have heads or tails on my first flip. Now I flip it again. So if I had landed on heads, the second flip would have been heads or tails. If I had landed on tails for the first flip, the second flip could have been heads or tails. And then we can do this one more time for our third flip, that we could get heads or tails, heads or tails, heads or tails, and then heads or tails. So what's cool here is that we can see really those specific combinations happening. So I could see that it is very possible that I could get heads, heads, and heads on all three flips, or tail, tail, tail on all three flips, right? So we can see those combinations happening, right? So here would be all heads, here would be all tails. So I could actually say, how many times would I get all three the same outcomes? So I would have 2 out of my 8 possible outcomes, right? So I can start to calculate those probabilities that it would be 2 out of 8. I can also look at things like how many combinations would have, 2 heads in it. So I could have heads, heads, tails. I could have heads, tails, heads, right? That has 2 heads in it. Tails, heads, heads, and that's going to be my only 3. So 3 of those combinations would have 2 heads in it. So we can start really looking, once we have that sample space in the tree diagram, at those specifics. So the tree diagram is really nice, again, for smaller sample spaces to really get that visual. Now for the next one, this one asks us to specifically use the counting principle, I'm still on highlighter, to show how many combinations you have with rolling a die 3 times. All right, so let's think about this. We're going to be rolling a die, so I have to think about how many outcomes can I have from that. Well, we're going to assume it's a normal 6-sided die, so there are 6 possible outcomes, right? I could land on 1, 2, 3, 4, 5, or 6. So do I want to list those out and then have to do another set of 6 branches off of my 6 first pieces, and then another set of 6 branches? No, that sounds terrible. This would be definitely a time to use the counting principle. So on my first roll, I could have 6 possible outcomes. On the second roll, I could have 6 possible outcomes. And then again on the third roll, I could have 6 possible outcomes. So how many combinations could we have? 6 times 6 is going to give us 36. And then we're going to multiply by 6 again to get 216 combinations. So again, I would definitely not have wanted to make that with branches, because I would have had 216 branches in my tree diagram, and that sounds like a nightmare. So using the counting principle is going to make our life a little bit easier here. So we can definitely use the counting principle for our total number of combinations, and we can use tree diagrams as well for that, for smaller sample spaces. The benefit of a tree diagram is that we can visualize those specific pieces and specific outcomes that we might want to look at. So that's a little bit better for probability. But if I'm just looking at total combinations, counting principle is a really nice way to calculate those things very quickly. So you have to, again, read very carefully as to what it's asking for, and you have to think very carefully as to what are your possible outcomes for each step of the way. I hope you guys enjoyed watching this video. Bye.